Okay, good afternoon. So we're back talking about algebra. We're thinking about solving equations, and this is just another step in the long series of videos that we've been doing so far, basically ranging about all topics that are polynomial related. So we touched on domain, we've touched on range, we've touched on graphs a little bit. We'll get to a little bit more of that at some point. What we're thinking about right now, well, it's generally been simplifying. Now we're moving towards simplifying in order to solve. And so what I want to reiterate is just formalize sort of the key idea behind factoring when it comes to solving equations. So why do we factor? Well, we've talked about it kind of at length, right? Of this idea that factoring is actually only valuable when we're interested in multiplying by zero. And we're only interested in multiplying by zero because it has a special property, which we can call the zero product rule. I've referred to zero as, an important number when it comes to multiplication and addition for that matter. So if two numbers multiply together to be zero, then either A is zero or B is zero. And or in mathematics, very precise word, it does not discount the possibility that both could be zero. That's perfectly fine. It embraces that A and B could both be zero. It's no problem. Still holds the zero product rule. But all you need is for one of them to be zero, and then it doesn't matter, right? In other words, if A equals zero, then A times B is zero, no matter what B is. And similarly, if B equals zero, then A times B is zero, no matter what A is. This is a fundamental fact. This is something about our number system that we hopefully feel very comfortable with at some level. Zero groups of a certain number of objects is just zero objects. And a certain number of groups of size zero is also zero objects. Any number times zero is zero. Results in zero. You have zero groups. So this is a formalization of that statement, saying that, if you're multiplying two numbers together, A and B, and those numbers multiply together to be zero, then either one could be zero, right? One of them has to be. Now, there's sort of a bidirectional thing that we should think about here. So not only if they multiply to zero, then either A is zero or B is zero. That's really important, but that statement is actually a bridge, one bridge farther than we may want to start here. So it has an implication there that actually when you factor, if you're looking at all the factors correctly, you are looking at all of the possible potential answers. If we also want to consider these two statements in tandem here and say to ourselves, okay, what factoring and solving equations is doing is trying to leverage these two facts. It's trying to say, okay, what I know is that if two numbers multiply together to be zero, one of them is zero. And further than that, if I know one of the two numbers is zero being multiplied together, then I know the result is zero. So this bidirectional type of thing is just trying to get us to say, Well, hey then, if we can make one side of the equation 0, and then write this side of the equation in the form something times another thing, then we can break the problem up by looking at A and B separately. So that's what we've been doing, and that's why it's incredibly important to make sure that you push the question, the equation, to make sure that 0 is on one of the sides. Because as we showed last time, a nice example of how if you aren't making the right-hand side say 0, then factoring won't actually clarify the equation at all. So for example, solve 2x minus 3 times 5x. Oh, accidentally shifted the screen there. Times 5x plus 1 to be equal to 0. Well, if two things multiplied equals 0, that will only happen if one of the two things are 0. Additionally, if two things are multiplied together and one of those things is 0, then you will get 0. So they are both the only candidates and they are potential answers. So let 2x minus 3 be 0. Then 2x needs to be 3, and x would have to be 1.5, or 3 halves. Notice that if x is 1.5, this term is 0, but this term is not 0. But it is still a solution to the question, because it's 0 times non-zero, but that result is 0, and that's what we need. We need the multiplication of the two numbers to be 0. We don't care which one is 0, we don't need both of them to be 0. So similarly, if we let 5x plus 1 be 0, we want to try to figure out when that could happen. Well, it'll be at x equals negative 1/5. And when x is negative 1/5, oops, sorry about that, then this is 0 and this is not. But the resulting multiplication is. So the answers here would be x equal 3 halves and negative 1/5. So it's a simple example, one that we've looked at or cousins to it many, many times. Now let's take a look at solve. Oops, I don't want to use green. (4x squared plus x minus 3 equals 0). You'll notice something here. This is a trivial multiplication of two things, right? We could say the left-hand side is this and say, okay, well, now I know how to find my answers. I just figure out when the factors are 0. It should be no problem. But you realize in this, why it's trivial, this is the same, so it's still equally as difficult to figure out when that's 0, and 1 is never 0. So the goal, this is where the intersection here of solving by factoring and simplifying really come together as ideas. We solve by factoring. We can do it because of the zero product rule, but it's easier to do because of simplification. What factoring does, it simplifies the degree of polynomials. So what we get here, we'll reset. Could be 2x and 2x, might be 4x and 1x. I believe it's going to be 4x and 1x. Let's make sure. That looks good to me as a factoring. So x equals 3/4, or x equals -1. Okay. So this kind of trivial factoring does nothing for us because we need it to accomplish something. We need it to accomplish simplifying as well as setting up a multiplication. Now we can set up a multiplication in a way that doesn't simplify, but that doesn't help us. When we can factor in a way that simplifies it, we can then solve two separate, simpler equations, usually directly. Okay, so the next question then, x squared equals 8x minus 15. When does that happen? Well, it might not happen at all, but if it does, potentially a nice way to find out would be to factor. However, we're only interested in factoring when it comes to solving equations when we can set it equal to 0. So we need to make that situation occur for ourselves by reorganizing the equation. And you can notice why we can really do this, why these two things are the same. Well, we want to know when this is true. But why are these the same things? Well, because we're saying when x squared is 8x minus 15, and then we're subtracting 8x and adding 15. So of course that's 0. So this is just an insight into some of the logic here of why these work, these rewritings. If x squared is 8x minus 15, then x squared minus 8x plus 15 is 0. So does this factor? Well, let's take a look. Yes. And we can see it. If I plug in 5 for x, I get 25 on the left. I get 40 minus 15 on the right. That's 25. Good. 3 on the left, I get 9. On the right, I get 8 times 3 minus 15. 24 minus 15, that's also 9. That's good. Done. So now the next layer, a question in the form that we haven't seen yet. Right, what have we seen? We've seen factored equal to 0, okay, great. We've seen unfactored equal to 0, okay, great. We've seen unfactored equal to something non-zero, okay. Now we're saying factored equal to non-zero. What do we do? Well, we have a problem. We can't just add 9 to both sides. I mean, we absolutely can. There's nothing wrong with it, but it won't help us, right? Because we'll get x minus 7 times x plus 3 plus 9 equal to 0. That's not a multiplication problem. It does not fall under the zero product rule because it's not the multiplication of things set equal to 0. It's actually multiplication and then addition of things set equal to 0. So order of operations being very important here. So what we can do, however, is take that somewhat counterintuitive step of unsimplifying or multiplying out the left-hand side. For what purpose? Well, in order to be able to combine the -9 from the right-hand side, with this polynomial in a direct fashion. Now we're set. Now we're set to go. Don't fall for this one if it's on the exam. Remember that you're interested in equations that factor on one side that are set equal to 0 on the other side. If it's already factored but not equal to 0, you're not actually close, right? If it's already factored and equal to 0, you're very close. But if it's already factored and not equal to 0, you're actually further away than some of the other questions where you have to factor, because you have to unfactor or multiply out, then write an equivalent equation, and then try to factor again. And it doesn't factor in the exact same way, as you can tell. It's not x minus 7 times x plus 3. That thing is equal to negative 9 when this thing, x minus 6 times x plus 2, is equal to 0. Of course, notice that we're able to do these rewrites of the equations because they maintain their consistency. Right? If you were to plug in 6 up here, you would get negative 9. And likewise, if you were to plug negative 2 in up there, you would get negative 9. And you better. Otherwise, solving this being equal to 0 doesn't help you understand when this is equal to negative 9. They have to be different form of the same balanced equation. Let's do one more. This real quick. All right. Last one for the day. When is one polynomial equal to another? When is one quadratic equal to another? Well, they might not be. They might only strike each other once, cross each other only once. They might cross each other twice. They could cross each other consistently if they're identical. But what do we have here? Well, two parabolas. Hopefully, this won't be surprising to you. The task is similar. We want to get an unfactored form of a polynomial to be equal to 0 so that when we factor, we can follow the zero product rule. Now, we don't have an unfactored polynomial equal to 0. We do have two unfactored polynomials. That's a nice start. Can we combine them? Absolutely, because we can add and subtract polynomials and their pieces. So we're going to subtract 3x squared, subtract 4x, and add 5 to both sides. Now, why did I pick this one and not the other? Well, like I could have subtracted 7x squared, subtracted 4x, and added 14 to both sides and gotten a 0 on the right-hand side. I pick the one where the highest degree term will wind up being positive. So that's subtracting 3 from 7, not 7 from 3. But once you pick one side, you have to continue with that side to make things equal to 0. So we very specifically picked those three things to add and subtract in order to make the left-hand side 0. The right-hand side looks like this. So the plus 4x and minus 4x balance each other to 0. They are inverses. So does this factor? Well, first of all, don't ever be concerned about rewriting an equation by flipping the sides. Perfectly fine. There is nothing important fundamentally about whether the left-hand side stays the left-hand side. You can flip them if you'd like. So if this is something that's more comfortable for you to look at, then I welcome you to change it. You can certainly solve it, however, as is. Via factoring, it's the difference between two squares. There you have it. And you can check that it does, when you plug in 1.5 to this and this for x, they spit out the same number. That is the task. This is the answer right there. X equal 3/2, x equal -3/2. So thanks very much for joining me. Look forward to the next one. Good luck with everything.